Ever questioned why understanding Boolean algebra and De Morgan's laws is crucial? Well, it's time we provide you with some insights. Boolean algebra is a mathematical structure that captures the essence of logical thought. It forms the backbone of digital circuit design, computer programming, and even the internet. In the heart of this algebra lie De Morgan's laws. These laws are not merely mathematical formalities, but fundamental principles that describe the relationship between the logical operations of and, Oregon, and not. Imagine you're building a digital circuit or writing a piece of code. Often you'll need to simplify complex logical expressions or optimize your design for speed or space. That's where De Morgan's laws come into play. They provide a systematic way to transform and simplify these expressions, making them more manageable and efficient. Let's break down these laws. There are two De Morgan's laws. The first one, De Morgan's law for AND operations, states that the negation of a conjunction or an AND operation is equivalent to the disjunction or an OR operation of the negations of the individual terms. In simpler words, the negation of the AND of two variables is the same as the OR of the negations of those variables. The second law, De Morgan's law for OR operations, is the mirror image. It states that the negation of a disjunction or an OR operation is equivalent to the conjunction or an AND operation of the negations of the individual terms. To put it simply, the negation of the OR of two variables is the same as the AND of the negations of those variables. These laws are so fundamental that they even hold true when we switch from digital to analog systems, from binary to fuzzy logic, and from circuits to code. They are the universal principles of logic. Now that we've established the significance of Boolean algebra and De Morgan's laws, let's delve deeper into each law, starting with De Morgan's first law, which revolves around AND operations. Delving into the heart of Boolean algebra, we find De Morgan's first law focusing on the AND operation. This law states that the negation of a conjunction or an AND operation is the same as the disjunction, an OR operation, of the negations of the individual terms. In mathematical terms, we express it as the negation of A and B equals the negation of A or the negation of B. To put it simply, if you have two terms, say A and B, and you're taking the AND operation of those two and then negating it, it's the same as taking the negation of A, the negation of B, and then taking the OR operation of those two negations. It's a little bit like saying, I won't eat an apple and a banana is the same as saying, I won't eat an apple or I won't eat a banana. Now, to solidify this concept, let's glance at the truth table for this law. A truth table is a mathematical table used in logic to compute the functional values of logical expressions on each of their functional arguments. In the context of De Morgan's first law, our truth table would look as follows. When both A and B are false, or 0, the result of A and B is also false, and thus, the negation of A and B is true, which is the same as the result of the negation of A or the negation of B. When either A or B is true, or 1, the result of A and B remains false, keeping the negation of A and B as true, which again matches the result of the negation of A or the negation of B. However, when both A and B are true, the result of A and B is true, turning the negation of A and B into false, which is once again the same as the result of the negation of A or the negation of B. That sums up De Morgan's first law. It's fascinating, isn't it? However, there's one more law to explore. Moving on to De Morgan's second law, which is all about OR operations. This law states that the negation of a disjunction or an OR operation is equivalent to the conjunction or an AND operation of the negations of the individual terms. So, how do we express this mathematically? Well, it's quite simple. If you have the negation of the OR of two variables, it's the same as the AND of the negations of those variables. In other words, if you have a negative statement about an OR condition, you can rephrase it as an AND condition involving negative statements. We write this as not A or B equals not A and not B. Seems a bit abstract, doesn't it? Let's break it down with a truth table. A truth table is a great tool for understanding logical operations. It shows all possible truth values for a given set of variables. So let's consider two variables, A and B. We'll look at all the possible combinations for A or B and then take the negation of that. The result is exactly the same as when we take the negation of A and the negation of B and then find the AND of those two. For instance, if neither A nor B is true, or in other words, if both A and B are false, then A or B is also false. But if we negate that, it becomes true. On the other hand, if we take the negation of A and the negation of B separately, both are true. And the AND operation on two true statements is also true. So, you see, both sides of the equation give us the same result. This little exercise shows us the power of De Morgan's second law. It allows us to transform a complex logical statement involving OR operations into a simpler one involving AND operations. That covers De Morgan's second law. With both laws now under our belt, we're ready to explore the concept of dual in Boolean expressions. Ever heard of the dual of a Boolean expression? It's a fascinating concept. In the realm of Boolean algebra, the concept of duality is quite intriguing and useful. The dual of a Boolean expression is simply obtained by interchanging and/or operations, as well as swapping zeros with ones, and vice versa. It's like looking at the mirror image of an expression, but in the Boolean world. Let's delve deeper. Suppose you have a Boolean expression featuring AND operations. The dual of that expression would be the same expression but with every AND operation replaced by an OR operation. Conversely, if your original expression features OR operations, you would replace every OR operation with an AND operation to get the dual. But that's not all. In addition to swapping ANDs for ORs and vice versa, the dual of a Boolean expression also involves interchanging zeros and ones. So, if your original expression contains a 0 in the dual expression, that 0 becomes a 1. Similarly, any ones in the original expression turn into zeros in the dual. For instance, let's say we have a simple AND operation A and B. The dual of this expression is A or B. Notice how the AND operation was replaced by an OR operation. That's the essence of duality in Boolean expressions. Similarly, for an OR operation like A or B, the dual would be A and B. And what about zeros and ones? If you have an expression like A and 0, the dual would be A or 1. The 0 has been replaced with a 1, and the AND operation has been replaced with an OR operation. This concept of duality is not just a theoretical curiosity. It's a powerful tool that helps us simplify and manipulate Boolean expressions, making them more manageable and understandable. It's like having a secret decoder ring for Boolean algebra. That's the dual of a Boolean expression for you. It's intriguing how these concepts intertwine, isn't it? We've covered quite a bit today, haven't we? Let's take a moment to summarize. We started our journey by diving into the fascinating world of Boolean algebra and De Morgan's laws. We learned that these are not just mathematical curiosities, but powerful tools that are instrumental in the field of digital logic design. We explored De Morgan's law for AND operations, which tells us that the negation of an AND operation is equivalent to the OR operation of the negations. In other words, if you have two variables and you negate the result of their AND operation, you get the same result as if you negated each variable and then took the OR operation of those negations. Then we moved on to De Morgan's law for OR operations. This is the mirror image of the AND law, stating that the negation of an OR operation equals the AND operation of the negations. So if we have two variables, the negation of their OR operation yields the same result as the AND operation of their negated values. Next, we delved into the concept of a dual in Boolean expressions. This is a simple but powerful technique that involves interchanging and/or operations and flipping zeros and ones. The dual allows us to transform and simplify complex Boolean expressions into more manageable forms. In essence, De Morgan's laws and the concept of the dual serve as vital tools for simplifying and optimizing Boolean expressions, making them more efficient and easier to understand. They are the bedrock of digital logic design, and understanding them will undoubtedly give you a significant leg up in this field. And that's a wrap on Boolean algebra and De Morgan's laws. Remember, understanding these principles will give you an edge in digital logic design and beyond. Thanks for watching, and keep exploring.